So the title of the talk is Powering India's Semiconductor Manufacturing. And this is the agenda. We want to talk about the opportunity for India, big opportunity, as you all know, which is why you're here. I'll tell you a little bit about Synopsys, Synopsys' manufacturing solutions. And within the manufacturing solutions, there are several that are very important for us to be able to deploy if we are going into high volume manufacturing. TCAD solutions, lithography and OPC solutions, process ramp solutions, product ramp solutions. So these are some of the components of a good manufacturing suite of products that we will need when we really are serious about high volume manufacturing. And then we'll summarize, and of course, we'll be very happy to take your questions. This goes without saying, India's opportunity in semiconductors is very big. And India's plan for self-reliance in semiconductors is both strategically and economically important. Strategically, for the obvious reasons, with the geopolitical situation in the world, each country needs to have its own source of this very important source of strength for the country, which is semiconductors. And economically, you see here that last year, India imported more electronics than oil. We all think of oil as a big burden for India, but electronics is a bigger one. So imagine if I didn't have to import electronics, we would save 55 billions of foreign exchange. And then you know this very well, as one of the fastest growing economies, the demand for semiconductors will continue to rise. So the new policy on semiconductors is very timely, and we're very glad that there's already been a couple companies who have announced manufacturing facilities in India. And Goldman Sachs forecasts that in 2075, India will have the second highest GDP in the world. It's an amazing thing, the second highest in the world, of $52.5 trillion of GDP, which is a fabulous number. And so we're on the right track for that. And if we can also make sure that India can manufacture and design its own semiconductors, that'll be wonderful. So semiconductor manufacturing is an exciting opportunity for India, and Synopsys stands ready to be a partner and a supplier. About Synopsys, just a couple minutes to tell you more about our company. Synopsys, you all have heard, is being in the business of developing tools for EDA for more than 35 years. For 35 years, we've had unparalleled growth to the point where EDA company in the whole world. And that has happened with a lot of contributions from our colleagues in India. Synopsys has been in India since 1995. We're now up to 5,000 employees. We have several patents filed from India at the US PTO and been granted. And we have a breadth of expertise in India: software verification, IP, design, and manufacturing. And so you can also see that we have offices throughout India. We can see the headcount in each place. So we are very excited about the contributions that Indian team has made to EDA and to Synopsys' success. And I think it's also appropriate now that Synopsys, in turn, participates in India's new initiative to become a semiconductor manufacturing powerhouse. So the thing that's unique about Synopsys, that will make Synopsys a good partner for all of you considering any kind of manufacturing, is that Synopsys is a full stack supplier in EDA. Everything that you can think of in EDA, you can get from Synopsys, from design capture all the way to silicon manufacturing, everything in between. And now we are working on what we call as a hyperconvergence. How do we bring these technologies together so that we can offer a better solution to our customers, and how we can use the power of pervasive AI to make each of these tools better? That's our That's our quest right now. The whole company is focused on this and executing really well on this stuff. And as you begin to engage with us on manufacturing, you'll begin to see some of the benefits of this approach we've taken. Okay, let me tell you briefly about Synopsys manufacturing solution. It's a very a large area, so I'm not sure I'll do justice to everything. But let me just high level tell you that you can think of manufacturing solutions as being composed of four important components. TCAD is number one thing, and you'll hear more about that. TCAD is what you use to actually develop your process. Mask fabrication. You know that before you begin to make your wafers, you have to have a mask, and I'll explain to you more about that. It's a very important, very challenging technology that Synopsys is one of the leaders, and we'll tell you more about how that works. Silicon lifecycle management is the process by which you can keep track of your silicon as it goes through manufacturing, but also when you ship it into the field. Even when your customer is using it, you can monitor it and decide what to do to mitigate any potential problems. So that's silicon lifecycle management. You need that. And finally, you need process control solutions to run your fab efficiently, right? You're now beginning to see discussions of fabs being built in India. The fab is built, it'll require a process control solution because a modern fab has of the order of 1,000 pieces of equipment. It costs billions of dollars, and it has several hundreds to 1,000 pieces of expensive equipment, and all of this has to be efficiently managed, and that is done by our process control solutions. So think of this as the introduction to our portfolio of tools to manufacturing, and allow me to now tell you a little bit about how all of this fits together. For most people who have designed chips, and that's the bulk of companies, right? Fabless companies are more numerous. When we think about manufacturing, think about designing a product, testing a product, and then going into manufacturing, right? So let me get my laser pointer so I can point you to what I'm talking about. So typically, always you design your product, you test your product, and then you give it to a fab, a manufacturer, where you have what is known as a product ramp. This is a curve that you're all very familiar with. Almost always, when you start manufacturing your chip, the yield is low, but very quickly it ramps up, and this part is called product ramp. Most people are familiar with it. But not only should we be aware of this, but we should be aware of one other thing that is just as important to manufacturing, which is the idea of a process ramp. What is process ramp? The idea of process ramp is that you actually design a process. By process, I mean something like a 28 nanometer node or 40 nanometer node, silicon on carbide technology, silicon, SOI technology. These are different processes, right? And if you are in the manufacturing business, you have to develop this process. That development happens with using TCAD, where you can do material design, research, process development. Then you go into lithography, where you decide what kind of lithography to use, and I will explain more about that in a moment. When you're ready with a process that looks like it's ready for production, you go into the fab, and here you have essentially an inverse curve of this, because on this curve, we are looking to push down defect density. That is missing from our axis. So think of one axis as being the yield. The more, the better, which is this blue line. The green line is defect density. The less of the defects, the better. So when you talk about ramping your process, you're talking about bringing down your defect density to the point where you can begin to, somewhere around here, you can actually begin to manufacture a real commercial chip. Okay, so remember that. There's two parts to manufacturing: process ramp, the product ramp. A product ramp is when you focus on, when you take an existing mature process and ramp your product, your new processor, your new GPU, your new FPGA, what have you. Process ramp comes before that. This is when you have nothing. You start with a clean sheet of paper and say, I want a 28 nanometer process. How do I design it? And so then you use TCAD and mask to design that. Okay. So bear with me on this. Hopefully you'll remember this as we go through, because we'll keep coming back to these concepts. So let's talk about TCAD. We mentioned about the fact that TCAD enables development of new processes in a cost-effective manner. Let's take an example. 28 nanometers, right? For most people, that does not seem as a very challenging node. Right now, people are designing at 2 nanometers, right? 14 angstroms. It's relentless, the pace at which things are moving. Yet, if today in India, we want to bring up a 28 nanometer process or a 40 nanometer process, we'll see that even that is very complex. Why? Think about a simple planar FinFET or a simple planar transistor of any kind, and think about all the things that you have to get right to build a 28 nanometer device. You'll see that you'll need a metal gate electrode. A polysilicon gate that you used previous generation is not going to be good enough. You need high K gate dielectric, because if you don't use a high K gate, you'll have a lot of gate leakage. You will have to deliberately put stress and strain into your channel so that you can increase the channel mobility. Otherwise, as the channel becomes smaller, you'll have second order effects that will degrade the mobility of the channel. And you have to think about how to mitigate some of the short channel effects that become more prominent when transistors become small. And all this is at 28 nanometers, which nobody thinks of as bleeding edge. So this gives you an idea of the kind of variables that you have to deal with when you're in manufacturing, and why you need TCAD, why you need a partner like Synopsys with a long expertise in this to help you get this off the ground. So, think of Synopsys TCAD as accelerating the process development of both baseline and derivative technologies. What is a derivative technology? We know very well. Things like low power, right, or higher efficiency, or high performance. These are derivative technologies that you create once you have the base technology working. First, you have 28 nanometer technology working. Then you say, well, I want a low power version of this. That's a derivative. I want a high performance version of this. That's a derivative, and so on. So each of these derivatives, it's easy for us to say that each of that requires you to go back and redesign your transistor, the one we saw on the previous slide. And if you try to do that by running wafers, it'll be very expensive, as you can imagine, because equipment is very expensive. To put this in context, a single stepper, a lithography piece of equipment, is $150 million. So you don't want to buy equipment like that and play with it. You don't have time to do research on those machines. You have to do your research even before you begin to go your fab and try things out. That's where TCAD comes in. So you can do, pathfinding research, which is what's known as DTCO, design technology optimization. You can do process development, which is what we talked about. You can do process ramp, and you can do high volume manufacturing. Okay, let's look at a couple of examples of that. I have to watch the time because I tend to run over. So I'll invite the moderators to tell me if we are running out of time. So here's an example. TCAD being used to optimize device performance. What do you see here? TCAD helping you do stress engineering, right? Most of us think of it as stress as a bad thing, but in some cases it's a good thing. In this case, you stress the crystal, your mobility gets better, and you have to do it just right, which is why you use TCAD, right? Or you have an ultra shallow junction formation, have to worry about source drains, extensions, yellow implants. You can simulate all these things. The key word to remember is with TCAD, you can simulate. You can actually come up with your own device, your own material. Voltage, what is the on voltage, what's the off voltage? All of this you can do by just simulation using TCAD. You can do gate stack optimization and so on. So I think you get the picture, right? Is that with TCAD, you can, and it says here, without running too many wafers. Of course, you have to run a few wafers to validate what you're seeing. So here in this example, you see that, once you do a calibration, which is basically creating a TCAD model, you take a TEM or a SEM image. You know what a SEM is, a scanning electron microscope. You put your wafer under a microscope, a scanning electron microscope, get the actual silicon image, compare it to your simulation, see if you're going in the right direction. If not, you iterate, right? So by doing this, you can first calibrate your process, then you can calibrate your device, and then you can see, what is the effect of, say, for example, the body effect. What is the effect of the DIBL on this device, and so on. So that way, you can actually reason about your device before you have run even the first wafer. That's a tremendous saving in cost, tremendous saving in time, and it allows you to do a lot more what if analysis. What if I do this? What if I do that? Trying to do all this in silicon is, like we said, very expensive. So that's that. If you can remember that one thing is that with TCAD, you can simulate your process, you can simulate your device, get IV curves. You can even export that into a SPICE deck if you want to do SPICE level simulation using our TCADs. So it's very cool. And so with TCAD, you can do efficient process derivative development. What I mean with that is you take models and so on, you can explore the process. We have a tool called Process Explorer exactly for that reason. A TCAD tool called Process Explorer that allows you to explore the process. And when you have something that looks reasonable to you, you create a virtual PDK. With the virtual PDK, you can actually try out your blocks, your standard cell blocks, to see what does the performance look like. What does the PPAC all look like? And with that, you can iterate. So you can first create some optionality. By that, I mean you create several options. And once you have several options, you create optimality, meaning you pick the optimal process that's good for your requirements. And all of this you can do just with simulation. That's the cool thing about TCAD. So remember that that's one of the first things you'll need to get to know. Please feel free to call us when you're ready for that, and we will give you our tutorials and our tools to get going. Okay. And lastly, on TCAD, something that's really hot these days, or really cool, depending on how you say it, is EVs, right? Electric vehicles. And electric vehicles need a lot of semiconductor content. You know that very well. And in this case, specifically, they need power semiconductors, which have a different kind of a profile than your microprocessor or your GPU. In particular, you have to think about um, um, about technologies such as silicon carbide, gallium nitride, and understand more about not just threshold voltage but breakdown voltage, right? And so this is also something that with our TCAD tool you can do. We have best practice documents that will help you to get or to get you going very quickly. So that's for TCAD. Let's talk about mask solutions. I should probably start by saying what is a mask, right? That may not be a term that you're very familiar with. but I'll tell you in a moment. So what do you do with mask solutions? You create a mask from your design so that you can go to volume production. What does that look like? So here you see a picture of a typical lithography piece of equipment. What you have here is a light source, right? It's a laser light where you can see of different frequencies. I'll talk to you about that in a moment. Um, and here at the bottom is the wafer on which you want to make your chips. How do you transfer the design from your layout onto silicon? The way you do that is by creating a mask. Think of this as similar to a negative in a photography process, right? Of course, these days, very few of us actually see negatives or think about the classical photography process. But you remember, right? There used to be a process where you would develop your film, get a negative, and then the negative would be exposed to get a real photo, as we used to call it, that people could carry around in their wallets. Now, this is similar to that. The mask is essentially the equivalent of a negative of your design. Once you make the negative, you can make billions of copies very easily, just like with a photo. Once you have a negative, you can make many, many photos without any trouble. So that is the process of creating a mask. Easy to say, but I'll tell you, one of the most challenging, complex things you can think of. Why? I'll tell you why. So look at this picture here. What is happening is that as we, I'll apologize that there's a little bit of a challenge in how I created the slide. But what you see here is that as we go down to smaller and smaller nodes, the wavelength of light that's being used to expose this wavelength of light we talked about is not keeping up. It used to be 365 nanometers, then we went to 248, then we are stuck at 193 for a very long time, 193. With 193, we were doing 40 nanometers. Think about the gap. It is like using a big paintbrush to do fine art. It's not possible, right? It'll all be very garbled, which is what's happening here. As you try to print this plus sign, let us say, as you go to smaller and smaller geometries, you'll begin to see that it prints very poorly. Here, it's not so bad. It still looks like a plus, right? Though you can see the line is pulled back here, which is not good. It is a corner rounding here, which is not good, but you can still say, okay, I can live with it. But then you go to a smaller node. So what happens? It's beginning to pinch here, right? The pinch means now it becomes a resistive conductor, which can increase your resistance, make your timing worse, and so on. And then you go to even smaller node, see what happens. It doesn't even look like a plus anymore. It looks like some modern art, right? You don't want this on your silicon. You don't want this on your silicon. It's not going to give you what you wanted. So how do you avoid this? That's what mask synthesis does. What mask synthesis does is that it understands that because of this big gap between the wavelength of light that you're using and the feature size that you're printing, you will have distortion, to put it simply, right? One other thing I should say before I move off of this slide is this is stopping at 193, but of course you all have heard of EUV, right? EUV sits somewhere down here because EUV's wavelength is 13.5 nanometers, very, very small, which is why EUV is so much better to make small geometry transistors. You want to make 2 nanometer node chips, you want to make 6 nanometer, 5 nanometer chips, you need EUV because EUV's wavelength is so small, 13.5. But remember, it's 13.5, it's still not 2 nanometers. So you still need the power of mask synthesis to create the masks. Okay. So let's see how this works. Going back to what we saw in the previous slide, if you want to print an L shape and you don't have any modification or correction, what you'll print is what looks like this misshapen thing. I don't know what to call it, but it looks very misshapen. That's not what you want. So to avoid that, what you do is you do what's called as OPC, optical proximity correction. OPC adds all these extra features to your L shape. All you wanted as a designer is a L shape. But what we do as a mass synthesis tool is we take the L and make it look like this. The corners, we add features. Inside, we actually remove features, right? And when with this kind of a mask, if you can expose it, then you get something that looks like an L. How difficult is this? It's probably the most computationally difficult process in EDA. What I can tell you is that for some of the advanced masks, you can use more than 1 million CPU hours for one mask. That's how complicated this is, because at every point, you're solving Maxwell's equations. You all remember how computationally intensive Maxwell's equations are. You have to solve each of them at every point. And of course, we found some ways to abstract it, but nevertheless, that's the problem. Now, as things have gotten smaller and smaller, we have to come up with newer and newer mask synthesis techniques. At one point in time, we just had to use the equivalent of what you see here, right? Adding some features around the thing that we call as mask model-based OPC. But since then, we have had a lot of new technologies adding new assist features. I don't have time to explain all of this for you, but I just want to give you a sense of the complexity, using something called double patterning. You use two masks to print only one layer. That's double patterning. You probably heard about it. ILT is a very powerful technology that's used of late to print. MEC, a masquerade correction, EUV, so and so on and so forth. So just this can take hours of discussion, one discussion, but we don't have time. But you get the idea. Mask synthesis is complex, necessary, but with a tool like Synopsys is mature and ready for your use. Again, just like with TCAD, when you're ready to use it, let us know, and we'll be there to get you going, because we have, the industry's gold standard in what's known as rigorous simulation, first principle simulation that will help you with development, it'll help you with pre-production process tuning, and it'll help you with high volume manufacturing. Okay. So Synopsys Mask Solutions is a full suite, full stack solution. So what you see here is starting with your GDS or your OSS that you taped out when your design was done, to making the mask, right? We talked about the mask, which then goes into the fab, and the fab uses the mask to make the chips. All the steps, the pre-OPC step, the OPC test step, the rule check. Litho rule check is like design rule check. In design, you do DRC. In lithography, you do LRC. And you do MRC, which is mask rule check. And then you actually create the data for the mask, and you then make the mask. That is a full suite of things you have to do to create a mask. And Synopsys has every one of these mature, available, and ready to use. Here are some references. We are the golden reference, the market leader for rigorous lithography solutions, is used by all leading edge foundries and IDMs. Our OPC is used at the majority of leading memory companies and the top 2 foundries. And our mask data preparation tool is used by essentially most mask shops in the world. And Smart MRC is one of our very strong tool that does your mask rule checking. So what you see from here is these are battle-tested tools, ready to use with an army of engineers, well-trained, including a lot of them right there in India, who can step up and help you get this going. Okay, so we talked about TCAD, we talked about mask. We are 37 minutes into the meeting, and we have 2 more things to cover, right? Smart manufacturing process ramp and smart manufacturing product ramp. So I'll go a little faster at this point because I'm running out of time. So what you're seeing in fabs, now they're called gigafabs, they're huge fabs, is that process complexity is increasing. data volume is increasing, the analysis time is increasing, and therefore the cost is increasing, which you don't want. You want to control costs, right? So what you want is to move from late detection of problems to early detection of problems to prediction of problems, right? Remember, we're talking now about yield on a manufacturing line, right? Which is very, very important. It costs $1 billion for you to build this line. You don't want poor yield. That's money being burnt. So you don't want to just detect a problem. You want to detect as early as possible. And ideally, you want to predict a problem coming up so you can solve before it becomes a problem. And Synopsys has an end-to-end solution for this also. You see a theme here, TCAD, EDA, we had end-to-end. TCAD, an end-to-end. Mask, we had end-to-end solution. For process control, an end-to-end solution. So, we can be your one-stop partner for all this stuff. What you're seeing here is that we can help with process control, with defect management, with root cause analysis, with decision support. Once there's a problem, what do we do, right? It's a very, very big search space for you to figure out what to do. We are working using AI ML to help you make a decision. Well, the problem is on this piece of equipment, go fix it, for example. And like I said, the holy grail is to go to predictive control, where we see problems occurring and mitigate them on the fly, right? So this is our full solution in process control. And we're very pleased that this is also in volume production. Several of our customers, you can see that more than in each customer, more than 10,000 pieces of equipment are connected to our tool, which means that we are dealing with petabytes of data. And with one customer of ours, we're dealing with almost 20 petabytes, right? With a P, petabytes of data coming off the production line, which we analyze, reason about, and tell the customer what to do to keep their yields going and keep the process active. Okay, very cool technology, mature technology, ready for you to put to use when you are in need for it. And the same process control solution I mentioned is usable not only in semiconductor chip manufacturing, it's also applicable to things like smartphone assembly. I know India now has iPhone assembly factories. That kind of a line can use our process control to improve the process. It's a process. Manufacturing is a process, whether it's a chip, whether it's an iPhone, it's a process. So you can use this tool, use our solution to improve your phone assembly processes. You can, if you're working on LED, which I believe is also the case in India, you can use it for that. Or battery assembly, right? Again, with electric vehicles, batteries are very important. I know India is also very active in battery technology. You can use our technology for optimizing your battery assembly line. So not only is this for semiconductor, but also for associated electronics areas. Okay. Now let me touch on the last of the four pillars, which is product ramp and high volume manufacturing. And here we talk about data analytics and yield enhancement. What is the thing you have to remember here? That things are becoming more complex. You have not only scale complexity, which means smaller and more, but also system complexity, which means there is a myriad kinds of things that are working together that you have to worry about. You have to worry about packaging, you have to worry about just workloads and how to deal with it. And our approach to solving this is to provide you what we call as a silicon lifecycle management tool, which will help you in design, in ramp, in production, and even in the field. Even after you made your chip and sold it to your customer, when your customer is using it in the car or in a data center, if they want to monitor the innards of the chip, so to speak, that's possible because with our technology, we provide monitors These are like probes that you can insert into your design when you're designing your chip. And we provide a database to access the data and analytics to analyze the data to see what's going on with your chip, whether it is in RAM, in production, or in field. Okay, let me explain that in a little bit more detail. So, like I said, the fundamental thing is during design, you have to insert in chip monitors. Once you do that, you are able to extract data. And you may say, what kind of data? It can be temperature, if you want to see how hot your chip is running. It can be voltage, it can be current, it can be, some reliability metric. All of this can be extracted from the chip just using the same IOs that you use for anything else, put in a data store, and then you can bring the force of our analytics solution. We have a sophisticated analytics tool that'll analyze this data and then provide you feedback so you can act on it. So you know that if your chip is running too hot, you can probably turn down the voltage or the frequency if that's what you choose to do. Or, you may have some other mitigation technique. Or, if this is out in the field and it's showing a reliability problem, then you can proactively, tell your customer, hey, this chip might fail. Why don't you bring it back so we can analyze what's going on with it? So this is the idea of silicon lifecycle management. You can insert, monitors or probes up front, and that'll allow you to analyze the health of your chip, let's call it that, no matter where it is. Very interesting, very cool technology. And you see a theme here, right? Just like what we did with TCAD, with mask, with process control. Here also you see that this is mature technology being used by over 37 customers throughout the world. 6 of the top 10 fabless companies use it. Fabless, IDM, foundries, they all use it. And you have some marquee names, right? So who's who of chip design using our technology to do this kind of silicon lifecycle management. And you will want to do that when you get to that point of actually wanting to reason about the behavior of your chip, even when it's in the field. So again, just like I said with the other 3 things, this is technology that we have. It's mature and ready to use. We have a large team throughout the world, but also in India, that can engage with you and help you get off the ground and up and running. Okay. So 46 minutes, that's pretty good for me. I usually run over. So let me summarize. India is on the cusp of becoming a serious player in semiconductors, right? You agree? I just heard from Sharat that the Prime Minister is coming to Semicon to inaugurate Semicon, which just tells me how serious India is about semiconductors. So that's very heartening. And electronics and semiconductor manufacturing benefits significantly by using software solutions because they reduce complexity, they reduce time to market, and they reduce cost. Synopsys is the #1 supplier of IC design and manufacturing solutions. Well, you know this. We are the largest EDA company in the world, both on the design side and the manufacturing side. We have a lot of expertise, a lot of good tools, and most important of all, the desire to work with you, the desire to engage with you, the desire to make your enterprise on semiconductor manufacturing successful. So we are eager to partner with thought leaders like you. That's why you're here in the seminar. You are the thought leader for India in powering semiconductor manufacturing in India. And we all look forward to working with you and making this successful. Thank you very much for your time, and I'll be very happy to answer any questions you might have. Thank you.